All right, hi everyone. So this is going to be a bonus video with some extra examples of using the integral test to check on the convergence or divergence of some series. So we've seen some examples in class, but these will be ones where the integration is a little more involved. And so the process will be the same, but at the step where we actually have to compute the improper integral, the integration is more difficult than some of the ones we've seen in class. All right, so let's start with this one. Let's determine the convergence of the series going from 1 to infinity of 1 over n squared plus n. Okay. So in this case, one thing that you can notice right away is that the sequence 1 over n squared plus n, that converges to 0, so we can't immediately rule out converging. So to use the integral test, what that means is we turn that sequence into a function of a real variable, so 1 over x squared plus x, and we look at this function. Before we actually compute the improper integral, there are 3 properties we need to check. So first is that it is positive, and we're going to say all this on 1 to infinity, so positive and continuous. And it might not be positive everywhere, and it won't be continuous everywhere, because you can put in 0 and -1. It does have vertical asymptotes, but if you're only putting in things bigger than 1, you miss the asymptotes, you're positive, so we get that. The other thing we need is that this needs to be decreasing. And this is a little less clear, but not too much more complicated. So in this case, the justification for this is decreasing since the denominator, x squared plus x, is increasing on 1 to infinity again. So this is a parabola. Parabolas aren't always increasing, but if you're putting in numbers bigger than 1, you're always getting bigger. So this says we can use the integral test. Before we do that, we'll go ahead and say, what is the integral of this function? And then we have to go back and remember what were our techniques of integration. So for rational functions, there's no u substitution we can do, but especially after factoring the bottom, x and x plus 1, this is a partial fractions problem. So we'll go ahead and do that. Since both factors are linear and non-repeated, this is a over x, b over x plus 1, clear those to get a times x plus 1 plus b times x. Take our good choices for x to substitute in. If we put in 0, that's gone. We just get 1. So a is 1. If we put in -1, then this term is gone. We get negative b. And so b is -1. That means the integral we're looking for, rather than this single rational function, this is 1 over x minus 1 over x plus 1. And this we can integrate using a logarithm or logarithms. Natural log of x minus the natural log of x plus 1. And for what we're going to do later, it'll be nice to combine this into a single logarithm, which we can actually do because we have logarithms subtracted. We can rewrite that as a single logarithm where we divide them. So this is a logarithm rule. One way you might remember it is if you're dividing inside a logarithm, you can break it up into two separate logs subtracted. You can also reverse that process. And to be completely correct, we'll put a plus c there, but we're not going to need it since we're really doing an improper integral. So this is our integral, which means we can go ahead and actually write down the indefinite integral, or the improper integral. We just did the indefinite integral. So this improper integral of our function from 1 to infinity, well, improper integrals are limits. So we're integrating from 1 up to t of 1 over x squared plus x dx. And this is the, well, to evaluate this definite integral, we need the antiderivative, and that's just what we spent some time doing. So this is the limit as t goes to infinity of that function that we found, the natural log of x over x plus 1 from 1 to t. Substitute that in to get the natural log of t over t plus 1 minus, if we put in a 1, we get a 1 and a 2. So the natural log of a half. And now we can take the limit of this. What happens is when we take the limit of the first part, we can bring the limit inside. So this really comes down to what is the natural log of the limit of t over t plus 1 minus the natural log of a half. And what happens is this is a rational function, the powers match, or you can use L'Hopital's rule. Either way, this inside limit is 1. And the natural log of 1 is 0. If you like, you can use one more logarithm rule. You can bring a negative up as an exponent. Negative, or 1/2 to the negative first power is the reciprocal, and we get the natural log of 2. Which, especially these last steps, isn't really necessary because when we're doing this, we don't actually care what the number is. So what do we end up doing? What do we use this natural log of 2 for? So what we get to say is that since the integral converges, that's this natural log of 2, we get a finite number. Then by the integral test, the series that we started with also converges. And that's the conclusion that we wanted to come to. So what the integral test says is that given those hypotheses on the function, positive, continuous, decreasing, the improper integral and, go back, the series either both converge or both diverge. And the way that we will be using it is, given a series, find the corresponding improper integral. So from the series 1 over n squared plus n, we looked at the integral 1 over x squared plus x. We evaluated that, we found that it converged, and the integral test says then that series you started with also converges. One important thing to point out though, is the series doesn't converge to the natural log of 2. So this value we get for the integral, that's not the sum of the series. What actually we did have done before is that the series actually converges to 1, which we found because it turns out to be a telescoping series, and for telescoping series, you can actually find the sum. The integral test doesn't give you the sum, but it does tell you if the series converges or diverges. Okay. So let me do one more example that has a little more going on, especially actually in the beginning part, checking these conditions on the function. So let's take our standard kind of problem. Let's determine the convergence of this series. I'm going to go from one to infinity n over e to the n squared. Okay. So this is more complicated looking than some of the series we've been dealing with. One thing that we'll want to think about is, so this is a video about the integral test. Why is this a good integral test problem? And rewriting this a little bit. So instead of this negative or this n squared, e to the n squared in the bottom, write it with a negative exponent, n e to the minus n squared. Writing into this form, what we can see is that if this was a function we wanted to integrate, it's set up for a u substitution. And that's really what you need to think about. If you're going to use the integral test, you need to go into it with an idea of how the integration would actually go. Now, it's not like it has to be immediately obvious how to integrate it, but like in the last problem, why the integral test worked was because we could look at it and say, this is a partial fractions integral. We have to do the work of actually doing the partial fraction decomposition and then integrating once we've broken it apart in that way, but you have an idea of what the integral would look like. And here, again, we'd have to check to see exactly what the integral ends up being, but we can see there's a u substitution. U is minus n squared, and its derivative is basically n, which we have up front. And as we develop more tests, we want to have a good idea of when is a good situation to use one test and when is it not so good to use a test. And for the integral test, it really comes down to, well, do these three conditions get satisfied for the corresponding function, and can you integrate it? So in this case, the function we're looking at is either of these forms. I'll use the fraction one, x over e to the x squared. And looking at this, two of the conditions are pretty easy to see. And we'll really just point out that we need to have these. So it's positive, continuous on, say, 1 to infinity. It's actually continuous everywhere, but we only need it this far. And as long as we're not putting in negatives, so that we're going to end up with a positive number. What's less clear is that this is actually decreasing. You can check with a use of L'Hopital's rule that the limit of this is 0, but it's kind of complicated and it's not as simple as the last example to see that it's actually decreasing. If you have a kind of complicated function, how you check it's decreasing is, going back to Calc 1, you're decreasing if your derivative is negative. So we'll actually take the derivative and check that past some point, the derivative is negative, so past that point, our function is decreasing. So we take the derivative, this is the chain rule, this is low d high, derivative of x is 1, minus high d low, this is the chain rule, e to the x squared times 2x, all over the denominator squared. Simplifying the top a little bit, there's an e to the x squared that can get factored out and actually cancel this e to the x squared on the bottom. So we'll say 1 minus 2x squared, e to the x squared squared. So we get some cancellation, which means 1 minus 2x squared over e to the x squared. So if we want to see where this is negative, well, the bottom is actually always positive. So it really comes down to where's the top positive. Sorry, where is the top positive and where is it negative? So remembering this process, set the top equal to 0, solve this equation, you get plus and minus the square root of 1 over 2. And if we take just in the positive direction, so there's 0, square root of a half. If we test these points, then actually our derivative is positive here. So it is going up, but then after that, it's going down, and it's always going down. So this means that it's decreasing on the interval square root of a half to infinity. So the square root of a half is less than 1. So this means that from 1 to infinity, it's all 3 of these. So we get to use the integral test. Before doing the integral test, because the integral is a little more complicated than just one of our integral rules, we can take some time to actually do the integration first. So we said before getting started, this is a U substitution problem. So U is up in the exponent, its derivative is negative 2x dx. We only have an x, not this constant, so we move that around, divided by negative 2. So substituting everything in, our integral becomes negative 1/2 e to the u du, which is its own integral. And then we can substitute back in u, which was negative x squared, e to the minus x squared plus c. So we can actually do this integral. So if we come down to it and actually do the improper integral of our function. So first up, improper integrals are limits, integrating from 1 to t, x e to the minus x squared dx. We just found the antiderivative. So what we're taking the limit of is as t goes to infinity is negative 1/2 e to the minus x squared from 1 to t. Now substitute these in, and for the sake of taking the limit, I'm going to write it without a negative exponent. Limit as t goes to infinity, -1 over 2 e to the t squared, then plus 1 over 2 e. Putting in a 1, we just get e, so we have 1 over 2e because the negative cancels because of subtraction. And right here, we can see the purpose or the usefulness of writing without the negative exponent. In this case, e to the t squared is going to infinity, so it's easier to see that this part goes to 0, and we're just left with this constant 1 over 2e. And so we get this answer. That number is great. We don't really care what it is, but we know that this integral converges. And we can take that and actually write this wrap-up sentence, which always needs to be here. So what we can say is that the integral converges to this 1 over 2e, but we don't actually care what number it is. So then by the integral test, the original series we started with converges too. But as we want to keep in mind, the series doesn't converge to 1 over 2e. Okay. So these are two examples of some more involved integrals or more involved problems involving the integral test. The process is really the same as what we've been doing in class, but we do have the techniques to do more involved integrals, and sometimes those show up. And the more involved integrals are really what let us use the integral test in a really kind of flexible way. Anything that you can integrate, as long as it's a decreasing function from some point on, is something that we can use the integral test for. All right.